Okay, this is Lab Basics. We're making hydrochloric acid today. I've just remembered, let me go and turn this background podcast off so you can hear what I'm doing. So we're going to make our kind of all-purpose bench acid. So I've got these laminated sheets with the recipes for most of the acids that we use for 1 molar. They're taken straight from the Kleep's recipe cards. And we're not actually making acid per se, that's just something that we say. We're actually just diluting concentrated acid down into bench solution, working solution, something that's safe for students to handle and that will react quite reliably. Hydrochloric acid is classed as a strong acid, so it dissociates fully. Conc acid is violently reactive, extremely corrosive, and very dangerous to breathe in. So we want to be really, really careful when we're handling this. So we've got gloves, we've got glasses, got a lab coat on, and we're doing it in the fume hood. Pour it nice and slowly. There is no rush. You do not want to spill it. You either bring it up to eye level or you bend down so that the bottom of the meniscus sits at eye level. The meniscus is the natural curve that comes from liquids when they're in a tight container. And this is to account for parallax error, and it's actually something that we have to teach the students in our specification. When you're done with the conc acid bottle, put it well away from you or put it away. I've got some sodium carbonate solution in there just in case anything goes wrong. If it goes really wrong, prepare for a hose down. So hydrochloric acid is hydrogen chloride gas that has been dissolved in water. So this conc acid is actually 35%. So the Kleep's recipe cards are actually made up to 84 milliliter, and that is because they're just accounting for different batches. You can buy it in different strengths, and also it dissociates over time and gets weaker as the hydrogen chloride escapes. I'm just going to show you the calculations that Kleep's use to work out these concentration values. And these calculations will be for if you have 35% HCl. Firstly, you'll need to know the density of HCl per mil. So here you can see that if you had 1 mil of HCl, you would have 1.18 grams for every mil. So if you were to times it up for a litre, that would be 1,180 grams in a litre. So then you need to know the molecular weight. So you grab your periodic table, you look at the weight of chlorine and hydrogen on the periodic table, you add them together. And so that will be, if you had 1 mole of HCl, you would need 36.45 grams of it. So if HCl was a solid, what you would do is you would weigh out 36.45 grams, and then you just dissolve that in a litre of water, and that will give you a 1 mole solution of HCl. But like we said earlier, our issue is that HCl is a gas that's dissolved in water, and you can buy them in different concentrations from different lab suppliers. So if we're talking about 35%, we actually only have 35% of that solution, which is going to be HCl, and the rest is going to be water. 65% of it is going to be water. So we know that 350 mil of that solution is actually going to be HCl. So what we want to do is we want to times 350 mil by the density 1.18 grams per mil, and that will give us 413 grams of HCl in that bottle. So now what we have to do is work out a way of taking the 36.45 grams out of the 413 grams in the bottle under the assumption that everything is evenly distributed. We know that in 1 mil of HCl, 35% of it is going to be HCl, so that is 0.35 for every mil. You know that HCl should weigh 1.18 grams in every mil. We want 36.45 grams a litre, which is going to be 0.036 grams for every mil, against what we have got, which is 0.413 grams in every mil. So we divide what we want with what we've got, and that will give us 0.087, and that will be mils for every 1 mil to make a 1 mole solution. So you would times that up for a litre, and that will give you 87 mil. So you'd measure out 87 mil, you'd add 1/3 of the final volume with water, slowly add your 87 mil, and then you top it up to the line and give it a couple of shakes to ensure even distribution, and that's how you'd have your 1 mole solution. Now, Cleeps adjust that concentration calculation to account for variability in concentration of stock, and for old stock, give 84 milliliter as the figure on the recipe card. In the grand scheme of things, these concentration calculations don't really matter, and you can just stick with the industry standard of 84 milliliter because everything is just subjective to the experiment that you're doing, unless you're doing titration. But what I'm doing is an experiment where they react this acid with different grain size of calcium carbonate chips. They measure the volume of gas produced over a certain amount of time. Now, the volume of gas and how quickly it comes out is so quick and so large that there's no way slight changes in concentration that they're going to be able to see that in their data. Okay, so that's why we measure out 84 mil. We're going to add some water to our volumetric flask, and we need to make sure that we add 1 to 2/3 of the final volume to the flask. Classic laboratory technician saying it is acid to water, never water to acid. We pretty much only use 3 of the strong acids, and that's hydrochloric acid, sulfuric acid, and nitric acid. Hydrochloric acid is probably the most chill when you add it to water. The other 2 are really, really violent. It also depends on how much you're adding. So if you're making a stronger solution, 2 molar, 4 molar, 5 molar, the reaction gets more vigorous. You add nice and slowly and try and get every drop of acid into there. A little twist of the wrist will make sure that the acid doesn't come out of the top and down the side. Slowly mix that in and check for heat. I've made so much 1 molar acid in my time. I know that 1 molar is pretty relaxed with HCl. But again, for the experiment that I'm doing, I'm not too worried about accuracy of concentration. If I really wanted to make it super accurately, I'd be using something like a graduated pipette. So I've rinsed the neck down with distilled water, and now I'm thinking about putting it on a stirrer. Add the flea and just slowly add water to it in between each step. I'm going to put that on the stirrer and just leave that because that's going to be kind of warm, and I want to get it down to room temp. That might take half an hour to an hour for it to get down to room temp. It's only a few degrees hotter with the amount of water that I've added. Like I said, if I was making a stronger solution or if I was making sulfuric acid, I might leave it a little bit longer. I'm just going to add a little water until just as the neck starts to come from the bulb of the volumetric flask. Final check for heat, and now I'm just going to leave that on the side. Just rinse that measuring cylinder out with tap water and make sure that's nice and safe. Solution comes off the magnetic stirrer, and I'll just grab the flea catcher. Dip the catcher in nice and gently and make sure I'm doing loads of distilled water rinses as it comes out. I want to make sure that every single molecule of HCl comes off of that catcher and the bar and goes into the solution. So very nice and slowly, lots of rinses, made sure I left myself loads of room. Again, I'm just being really generous with the rinses to make sure I've got absolutely everything off of there and it's nice and clean. But also making sure I've still got lots of room before the final graduation line on the flask. Bring that up to eye level, making sure that that meniscus sits on the line. Point of pride for lab technicians, making sure that that meniscus is dead flat on the line. Taking my time here, you can add, but you can't take away. Now we want to fasten the bung and we want to do our inverts. Now, one time I've made a solution in a rush where I didn't do any inverts. They were titrating it and all of them got really crazy results. That was because I forgot to do my inverts afterwards and it was not evenly distributed. Permanent marker, all unmarked solutions contain a fast-acting poison that will kill you instantly. These are all things that you learn from experience. You've got to make those mistakes sometimes. Big H, big C, little L for HCl. And now we're just going to do our inverts. So 10 inverts, nice and slowly, making sure that bubble goes all the way up and all the way down. Couple extra for luck. That's 1 molar HCl. That is our absolute bread and butter for school laboratories across the UK and across the world. Those concentration calculations are there for just anyone who's curious. Hopefully that's helpful for anyone who's starting out. And that is my acid bottles topped up, ready for my experiment. We'll see you guys in the next one. Bye.